One thing you notice is that this relation can be realized by x being a derivative. So this is just the usual Heisenberg commutation relation, xp to the I bar, right? And then one of those is realized as derivative. So this two-dimensional, for example, xi xj to the I theta, you can use half of the coordinate as position and the other half as coordinate as momentum, just in quantum mechanics. Now, then when we say we push it or we disturb it, what we mean is that we do a fluctuation around the solution. So we give a push. So we denote the fluctuation as A. So the capital X, when A is 0, is just a solution. So that's a vacuum solution. And then now you give a fluctuation. And now because this X is like a derivative, so the X actually behaves like D plus A. Right, and ignore all the theta and stuff. But basically the idea is that this like D plus A. Of course, this is just a covariant derivative. So now we remember that in the original BFSS quantum mechanical action, you have a potential. The potential is basically the commutator square. Now, if X is given by a covariant derivative on the non-commutative space, then XX commutator will be given by a field strength, the Yang-Mills field strength on the non-commutative space. And similarly, you can complete the Lagrangian using supersymmetry. But those are not. So these two lines are not important. But if you look at just the bosonic potential, then you get F squared. And then the rest you supersymmetrize. So basically, the BFSS solution, BFSS, the M theory on a solution of the non-commutative space gives you non-commutative Yang-Mills. Right? So we generate a physical system in this sense. So we start from just a quantum mechanics without space, we have a time but without space. But then on a solution of non-commutative space, we generate a physical theory. So that gives the possibility that you may generate the world, four-dimensional world, from a theory without space or time. It's just because we are looking at a solution. Around this particular solution, we have space and time. So the space and time emerge as a property of the solution itself. So this is what Seibert discovered in the year 2000.
Excuse me, I'm confused with your first formula.
Yeah.
Yeah, so isn't xi is a space-time coordinate?
Yeah. In this case, it's just a space coordinate, no time.
Yeah, space coordinate. So
yeah.
Why is the formula to
Why is that this one?
Yes.
So I mean, I'm trying to simplify notation, but basically, if you have x1, x2 here, let's say two coordinate equal to I theta, then you pick x1 equal to derivative of x2, and then you keep x2 as a coordinate. So half of the coordinate you make it as a momentum, then you can realize this relation. Yeah, that's what I mean. Yeah, I mean, if you really look at this, it sounds crazy because if both x are like derivative, then of course you don't get any thing on zero. But what I really mean is that only like quantum mechanics, half of the coordinate, space coordinate, the other half are momentum. So these are like phase space, realized like phase space in quantum mechanics.
So you make the analogy of Heisenberg concept.
Yeah, like a Heisenberg continuity relation. Yeah. That's not easy to treat here. Okay. So in this case, actually space, not space-time, but actually space itself, because in the BFSS matrix model, there's a time already. But there's a generalization of that matrix model to something without even time. So in fact, you can derive both space and time, and its property. In this case, the property are the dimension of space-time and the non-commutativity from the solution dynamically. So the fact that you can, and also some people actually did Monte Carlo analysis comparing different dimensional space-time to energy, and then find that the four-dimensional one seems to be more favorable. But okay, these are like experimental effort to try to confirm four-dimensional. So I don't think this is very serious, but at least I think the important thing is that this kind of question can be addressed in string theory, and there's a framework which allows you to do analysis like this. How much time do I have? About time. So I have to generate time. Okay. I think I just show you picture very quick here. For 5 minutes. So you probably heard about holographic principle. It's a principle of proposal that gravity could be not fundamental, but described in terms of some degree of freedom on the boundary of the region. So it's like this picture here. The room, everything in the room actually can be represented on the surface of this crystal ball. So in this case, the hologram is this surface here. In that holographic principle has remained a principle for many years until 1997, when Asana found a concrete realization in string theory. So in this realization, which is called ADS-CFT, so I don't want to explain it in any detail, but basically it's saying string theory in a space which is called anti-de Sitter space. So it's a particular theory of quantum gravity. Is dual or is completely explained equivalent to another theory, which is a conformal field theory. It's a quantum theory living on the boundary of that space, and it's a non-computational theory. So in this case, a hologram is a conformal field theory. So I try to capture why it's not my invention, but I got it from somebody else. So this is supposed to be the picture. So this is the world is the soup, the can of soup, and the gravity is the content here. So according to the holographic principle, the gravity, you can explain everything about gravity without actually looking at the gravity itself, but you can get everything from the boundary, which is in this case the label. So you don't have to know the content of your soup by tasting it. You can just look at the label, and then the label will tell you everything about the gravity field. This is supposed to be a picture. But actually, I think I don't trust this picture anymore. Not because this is wrong. The physical picture is still correct, but I don't trust the label. There's a lot of problem in food industry in the world. So I think we need to be careful. But there's a lot of interesting application of this ADS-CFT correspondence. They're experts in this department doing this kind of thing. So I would just say, okay, you can change what you want for the gravity theory, and then you can have different holograms. And the hologram can be modeled in such a way that actually can do something interesting. So, for example, the hologram can be something about nuclear physics or condensed matter physics or plasma. So let's give a new type of application about string theory, which is to address this kind of strongly coupled phenomena using string theory, using the string theory language. So I think this last part I will skip because I really don't have time. So conclusion. So there's been a lot of progress in the understanding of geometry and string theory and symmetry in string theory, and these are novel because all these properties which I talk about are not realized in a theory of quantum particles. They are realized in string theory, making use of essential property that give a fundamental extension instead of a quantum particle. Also, there has been a lot of interesting mathematical spin-off during the development. Now, string theory up to now, I think 74 until now is about, well, actually more than 40 years, more like 50 years of development. Right? We are still far from a complete satisfactory formulation of string theory. So what I mean is that we now have something like M theory, and we have a definition of in terms of the quantum mechanics. But honestly, we are still very far away from being able to prove it or being able to use it to do anything useful. Like for example, to tell what's the nature of Big Bang singularity, that kind of question. So Carl Sagan once said a remarkable claim, we need remarkable proof. Basically, just mean no free lunch. So I think what string theory is trying to do certainly is remarkable, maybe more than remarkable, right? Too good to be. But so I think it's worthwhile to remember. Although we are still far from having a completely satisfactory formulation, but we are still learning a lot of things, and hopefully those things will be useful for the final answer. And in terms of the time scale, I think 50 years is actually not very long. If you remember, I tried to make a table here about the development of quantum mechanics. So the backbody radiation, the problem with backbody radiation was first, at least historically, officially recorded by Kirchhoff in '59, and Heisenberg, uncertainty principle was written down in '27. So that's kind of 68 years. I think I'm right. Yeah. So that's a long time before you actually arrive at the formulation we have today. And in between, there's a lot of development in quantum mechanics. Now we learn it in textbook, but actually it's not fundamental. For example, the Bohr atomic model, right? So this thing, of course, it plays some role in the development, but at the end, I mean, this is a fundamental formulation. The Bohr atomic model, of course, is interesting because it tells you about eigenstate and eigenvalue. So I hope in the development of string theory, it will be like this. Many things we learn today probably are not going to stay at the end. But hopefully something will stay. Some key concept will stay. Like for example, this I just said the atomic model of Bohr. Some key concept like eigenvalue, eigenstate stay until the end. So hopefully something we do today will remain. And also another amazing thing is that string theory does provide us a fundamental framework which you can address some of the questions which we cannot ask or even think about otherwise. So I think one of the ways you can characterize the development of science is that we actually learn to ask smarter and smarter questions which you cannot even think about before. And that's certainly true in string theory. But the question is that have we asked the right question? So I think it's fair to say, actually, I think also encouraging for the young people here, you should expect, the answer should be no, and you should expect an expected question to come anytime. Yeah. So I hope some of you will be able to ask the right question and the remarkable question and I have the privilege to experience that in my lifetime. Thank you.
Do we have any concrete prediction of the string theory?
No. So I got this question very often. So, but I think if you can think about it this way. So we start from, of course, there are many ways to build a theory. The way string theory try to build a theory is from the so-called from the top down. So you build from the fundamental assumption and then you go down. The way most of the other theories we know about is bottom up. You start from things you know and then try to build more and more, make it more and more fundamental. So that is actually easier to ask to predict something. And yeah. To cosmology to what? The window.
Yes.
Yeah. Of course So everything finished that comment first. So for string theory is top down. So it's a long way. I mean, like climbing a mountain. It's a long way. If you climb up to 8,000 feet, it's a long way between 8,000 feet and the ground. So there's a long development of things. So I think string theory has the right ingredient. I mean, could have the right ingredient and framework to answer this question, but it take probably a long theoretical development, technical complication before you can actually find something calculable in technology. But okay, about cosmology actually is a very good thing. So one problem with string theory or testing string theory is that string scale is very small. So it's hard to make a prediction which can be tested in experiment. But inflation. So let me but we know there's an inflationary scenario. Inflation is characterized by the fact that universe expands by huge scale in a very short time. So something very small, even if the signal is very small, has a possibility to be expanded to an observable scale. So some of a lot of effort spent on string cosmology has been spent on string cosmology in the last 10 years, 15 years or so related to inflation. So inflation becomes a window to look for a signal for string theory. So string theory has a mixed prediction about observation in cosmology. But unfortunately, so far, the observations are consistent with the standard model of inflation. So we don't see any signal for a string yet.
Okay.
Yeah.
Since the string theory, you include the space-time and also like the mass, spin of those properties. How about the charge? Can the charge be included or explained by the string theory?
Of course, yeah. Charge is just an interaction. So the simplest kind of charge, the electric charge, is just
no, but it's quantized and with different, we have fractional charge and also integer charge.
Yeah. So the simplest charge is the charge in front of the coupling of E, J, A. But in principle, what you mean by charge is the representation, right? It's a representation content.
Well, it definitely is it's how should I say? I mean, any particles, right? They have a charge, so it's their property. It's a very fundamental property, just like spin and mass.
In principle, all the properties can be explained in a string phenomenological string model building. But so one can write down a string model of, for example, D-ring using D-ring, arranging the ring in different angles. Those angles will give you some values of the two-power coupling or the charges or the masses. So that part can be calculated, and that part can be invisible. That's nothing. Which,
for example, can string theory come up with a fractional charge in calculation, in prediction?
You mean other than QCD, the quarks?
Yeah, the quarks.
Oh, yeah.
The quark charge.
Okay, good. So that's come to the. So I say, in principle, one can write down anything which will produce the standard model, but then there's a whole bunch of other constructions which give you other picture, which doesn't look like the standard model. So the question about string theory is that there's no problem to write down something which looks like the world, but we don't know why do we select this. So that's the problem about selection. So if you tell me today, actually there are fractional charge in nature, then string theory will go back and then we modify the calculation and then come up with a model which explains that. But the question is still, we don't know why that, we cannot, because for us it's not just about model building. We want to have a fundamental understanding why that particular vacuum is picked rather than another. So that part is not understood, and that's a very important question. And I understand what you mean. Yeah, you're right. That's a fundamental problem. But that's again, I think in principle one can try to include some non-additive effect in string theory, and then leave the vacuum and then take the correct vacuum. But so far that hasn't been achieved. Yeah. So
I have the same question as him. But I may put it more precisely.
Yes.
When you talk about electric charge, it's real existence, right?
Mm-hmm.
And do you have to put them into your theory, or your theory will generate its existence from your theory?
No, we don't have to put them in. So the way
it will generate from your theory.
So the way it works, I have to put in something, of course. I have to put in one type of interaction, and then presumably all the interaction, the charges and for example the Q, and they will generate.
Artificially put it.
I put one. Yeah, I put one type of interaction. That's a string interaction. So like two string can scatter and then that's just
up to now you have not realized that.
What?
Realize in a theory that will generate electric charge.
No, you can. You do. You can generate electric charge. You can generate electromagnetic interaction on the assumption of one universal interaction, string interaction. So what I mean is that you can generate all the different interactions in gauge theory, in hex, invisible, in hex, and then from one interaction.
But in a mathematical model, when you put into something, you generate something.
Yeah.
But what I'm talking about, will something spring?
You're going to get nothing to something.
Automatically jump out of your theory.
Yeah, but I think
that's the merit of a theory.
That's really a miracle. I think if you can get from nothing to something, that's really miracle. You have to start from something. I think for theoretical physics, the hope is not to explain, not to have magic, but to simplify, to have a simplified picture.
In BFSS, is the time the emerging quantity?
Time is not emergent, but that's a generalization or alternation to the BFSS matrix model. This so-called asynchronic matrix model of IKKT. So that in there is even the time is not included. So it's a matrix, just a matrix model defined as a point. So for those models. So in that case, even time is generated.
So, maybe my question is more artificial. So, what do you think is the most popular problem in the string theory recently? So popular, I mean the both important and doable, because there are some problems that is important but not doable in current time.
Yes.
So what's your opinion?
If I know that the problem will be doable already, will be in the archive. So
No, it's not yet on the iPad, but now it's.
I mean, you want to, the way you ask the question is like you want to invest in the stock market and you want to know which one is the most profitable stock and you want to invest before everybody know about. So I think it's difficult, and so I think that question is not easy to answer. I mean, if people not.
I think it's a private question. Should ask him later.
That's a
collaboration.
That's a trend. Most of the people are working on the ADS-CFT, and because that's capture something about holographic principle, and that's supposed to hopefully give us some understanding about this actual quantum gravity. So a lot of people are working on that kind of problem. But yeah, and the rest we have to do it in Python.
Thank you very much.
Okay, let's thank Professor Chu again for a very wonderful talk.